thanks everybody. Let's get started on this competition, which is the TensorFlow Speech Recognition Challenge. It was sponsored by Google, hence the name TensorFlow in the title, I guess. It is about speech recognition, but it's a very constrained and simplified version of speech recognition, as you'll see. So this is not touching on the full-blown automatic speech recognition that'll do entire sentences and things, which would be quite a difficult competition. The goal is to create an algorithm that understands simple spoken commands. What does that mean? That means we've got a very small vocabulary of words that need to be identified. The input data, and we'll hear some in just a minute, is a very short audio file with just one word being spoken, and you have to identify that word. The idea is, if you want, I mean, it's kind of a demonstration project in a way, but if you wanted to build a command interface with voice input, this would give you a starting point for how to do that. And you want to, I don't know, control something on the screen just by saying up, down, left, right. This is the sort of commands that this competition is intended to figure out. In fact, there are the 10 words there: yes, no, up, down, left, right, on, off, stop, go. There's two additional categories: silence and unknown. Silence means there's no word there, although it doesn't necessarily mean quiet. It just means there's no words there. And unknown means there is a word in the recording, but it's not one of those 10. So we just put it into this bucket of unknown. So let me flip over here to something where we can listen to just a random sample of some of these things. Question, yeah?
Do we know how many different people are speaking?
Many different people. They sort of crowdsourced the data. And in fact, they're still collecting data for this set. They use this data set for demonstration code and so on. And you can go online. I didn't post the link, but I'll post the link. You can go and you can record your own voice saying all the words that they want you to say. Yeah. That's okay, because that's this thing. Okay. So in a second, you should hear it, like right about now. Did that make even a little dent? That was pretty quiet, right?
Yes.
Whoop, that was really loud. Okay.
Two.
These are from the test data set, the ones where we have to make the predictions. Let me,
Sounds like it's clipping.
yeah, it's maybe the venue's clipping a bit, but it's a little challenging here. It's really loud. Let me turn it down. This thing is on it's on some sort of exponential scale, not logarithmic. See if this one's any better. That's an example of background noise, as is that. So this is what silence sounds like. That one is supposed to be silent, but they said something.
Free.
Funny? Yeah, okay. So that's a quick sample of some of these. I wanted to get some better sounding ones, but oh, here we go. This is the one I want. This is the actual training data.
Two.
Oh.
Two.
Backward.
This one's silent.
No.
No.
Three.
Two.
Go.
So you can hear, unfortunately, the samples that happen to pop up in my random number generator were all kind of bad. A lot of them are much clearer than that, but there's definitely lots of noise. These are people just recording whatever on their phones or their computer microphone. So you get a crazy array of interfering noise, low levels, background sounds, all sorts of things. Yes. Was what given? No, there was nothing like that. Yeah. Could have come from any device. I don't know if they even know what the handset information was. Yeah. No, the only data you're given is the audio file and then the label, the word that it's supposed to be. Let me just go back a bit. So what you submit once you make your predictions is just a CSV file, and each row corresponds to one of the test data points, and it's just the name of the file and then which of those 12 categories that it's in there, that you think it's in. And then you're evaluated by, they just see how many predictions you got right versus the total number of predictions. That's a percentage. That's your multi-class accuracy metric. That's how you get evaluated. So the top 10 solutions ranged from number 1, who got a little over 91%, down to the 10th place winner, got a little under 91%. It was pretty tight. The top 3 solutions differed by only like 5 words out of maybe 50,000 that were being predicted. Somebody in the forum said it was only 1 word difference, but I don't know, I did the math, I couldn't quite get that. But anyway, it's just a couple of things. So it was very, very close, and I think the exact ordering of who came in first or second probably has a little bit to do with luck. Yes?
Do we happen to know how well humans do on this data set?
Only sort of anecdotally. I've listened to a lot of these files, and I would say that I'm probably good to 96, 97% maybe. And there's a fair number of mislabels. I think when people, I haven't gone through the process, but I think when they submit their recordings, they're told to say, say the word forward, and they say the word forward, or maybe they say something else. Maybe but it gets the label forward no matter what they uttered. So there's a lot of noise. Yeah, Matt?
What about class imbalances?
It's pretty balanced, and I've got a few slides on that, but it's pretty balanced between the words that we're supposed to predict, but then there's a whole bunch of words that are not, they're outside our set of 10, like a lot of those. So there's an imbalance in that sense. Plus, they didn't actually give us any files that were labeled silence. So we'll hear more about that in a minute too. Yeah?
Is there some additional information on, let's say, number of CPU used or like total time for processing?
There is, in a very special way. Let me come back to that in just a minute, because that's one of the interesting things about the competition. That usually there isn't that kind of constraint, but in this one there is. For those of you used to looking at Kaggle leaderboards, there's the top 10 people. The winners, number 1 is a team of 3 people. Heng is Heng Kerchang, who if you hang around these competitions, you would have seen him before. He was kind of amazing. He was really good. He had a whole bunch of great ideas. And he was basically almost like live blogging what he was doing. He was posting so much about it. So when it came time that he won, people will often post their solutions, and he posted something and said basically, well, I've already told you what I did all the way along. But he added some more information too. But it was great, and everyone was so grateful for what he did. If you haven't done a Kaggle competition or been involved in anything like this, or even just the world of data science, you'll probably be surprised by how much cooperation there is, information sharing, willingness to help people learn, how much of that goes on, even though it's a competition for real money and so on. They're competing, but everyone's willing to help everybody else out for the love of data science. Okay, on to this issue of, are there any constraints on how much processing you're allowed to use? And the answer is yes and no. There are actually 2 categories of prizes. There's $25,000, which gets split between the top 3 teams that just did the regular competition. But there was a separate category where if you get your algorithm to run on a Raspberry Pi, and then the winner there's just one prize here, like gets another $8,000 or gets $8,000. This is where the constraints on processing come in. I mean, first of all, the Raspberry Pi can only do so much, but there was explicit constraints like the maximum memory is like 5 megabytes of memory, and it has to run run in less than 200 milliseconds
So
on a Raspberry Pi.
you run the algorithm that's already trained on the Raspberry Pi. You don't have to train it on the Raspberry Pi, right?
You don't have to train it on the Raspberry Pi, you just run it.
That's slightly easier.
It's much easier. Yeah. Much easier to just run it rather than train it. The other interesting thing that's a little unusual in this competition, it's not unheard of, is that the organizers, again, folks at Google, provided some pretty good tutorial code to get people started. And I thought that was especially helpful here because audio has some unique aspects to it. You don't want people kind of wasting time just doing a learning curve at the very beginning. So they got everyone over the hump of that. And I think it was a good move because they got lots of people participating and lots of interesting ideas that came from people who know nothing about audio processing to start out with. So over 1,300 teams, that's a good turnout. That's the prize money. As it happens, the first place winners of the regular competition were also the winners of the Raspberry Pi prize. And the story behind that's pretty interesting, so wait for it. And we'll see. I hope I can get through all my slides here because this was a really good competition. So this is a classification problem is the way to think about it. This is not a regression problem, or it's not trying to clean up audio or reduce its noise or anything like that. You're just listening to the audio and then you just apply a label, one of these 10 or 12 labels. So in that sense, it's a very limited case of speech recognition. And it's much more like an ImageNet competition where you're given a picture of something and you say, what's in this picture? It's a dog, it's a cat, it's blah, blah, blah. I say it's sort of like MNIST for audio. If you're familiar at all with image classification neural network things, you'll know that MNIST is kind of like the hello world of that problem space. It's the first thing everyone uses. It's a problem set that's been around for a while, data set. And it's a nice, easy one to get started on. And when you're getting going with anything new, often you'll try it out on MNIST first. People have asked me, because they know I fiddle around with audio, so what's the MNIST for audio? If I'm going to get started, how do I get started? I think this competition, for the first time, gives you something like that to work with for audio. So that's cool. But the fact that it is a classification problem, sort of like an image classification problem, makes you wonder if can we transfer what we've learned about doing image classification, which has gotten quite sophisticated and quite accurate, can we transfer that into this domain? The answer is sort of yes and no. Part of the no is that there is a restriction in the competition. You're not allowed to use any outside data. You can only use the data that was given to you. That includes you're not allowed to use a model that's been trained to classify images, start with that trained model and then tweak it. That was out of bounds for the competition. So the real answer to the question, could we use a pre-trained image model and do amazing things? We don't know the answer based on this competition, but they wanted people to start more from scratch than that. Some of these competitions they're all fun in their own way, but some have problems and so on. This one was fun, so I was on a team that participated. It was great. It was very well organized. The data was good quality. The interaction with the hosts was good. They answered questions, and so many competitions, these are complicated things to set up. So many competitions have problems in them that they just kind of take the wind out of your sails when you're partway through and you realize they have to kind of reboot it and whatever. This wasn't like that. It didn't have any of those kind of problems. But I'll say, as fun as it was to participate, it was even more fun afterwards to read the variety and breadth of solutions that people tried. And I learned a lot of new things by reading what other people were doing. Maybe you'll learn something tonight too. Okay, let's look at some facts about the data, just to give you the general landscape of the nature of the problem. So you get about 65,000 training samples. That's a pretty good, healthy number. But not so large that it becomes a problem to train them all. 160,000-ish test samples. So you have to make 160,000 predictions once you've trained your model. They were, when you get evaluated though, they don't use all 160,000. I'm not sure if they told us how many, maybe it's 30% or so. So maybe 50,000 got used for the evaluation. The others are there to just kind of bulk up the number of points so you're not tempted to cheat and do a whole bunch of hand labeling, listen to it and put your own labels on it and so on. As I mentioned before, there was no data that was labeled silence. So we all had to figure out what to do about that. They did give us these background noise samples, and most people, including us, they were a couple of minutes long. Chopped them up into audio files about the same length as the training audio files and labeled those silence. And there were some other ways to deal or to come up with silence files, but I'll come back to that. Yeah, Anshan.
Anybody voice alignment to put silence before and after, and then have an HMM figure out here?
So there was nothing like forced alignment. I mean, we did a little bit. I thought it would be important, I'm not sure it was, but to kind of center the sound within the middle of the file. And again, I'm influenced by the image classification things. You look at MNIST and all these other things, all the interesting objects are kind of in the center. And it probably helps the model a little bit not to have those kind of random changes. But nobody used the phrase forced alignment. Yeah?
So it's called the TensorFlow challenge. Do you have to use TensorFlow?
No, although maybe for the Raspberry Pi one, I didn't look at the rules that closely, but they give you a kit to deploy in Raspberry Pi, so they made it super easy to do that. There were a few PyTorch solutions, but mostly people did seem to be using TensorFlow actually, and Keras on top of TensorFlow. Right, I mentioned the data for the 10 target classes was pretty well balanced, so that was nice. That's another problem we often have in competitions, is really unbalanced data. The unknown category, though, is a little problematic. There's a question of what you do about that, because you take all those, so you have a total of 30 words that have labels in the training set. 10 of those are the ones you want to predict, 20 are other things that are in the unknown category. So you just cluster all those 20 things into one bucket called unknown. It means you've got 20 times as many things in that bucket as you do in the other individual categories. So what's the best way to handle that? And people had a few different approaches on that, which I'll talk about. No data leaks, yay. The issue of silence was a little bit of a weak point, I think, in the competition, because we never got a super clear definition of what's silence or not. So I think most people concluded that it kind of goes like this. You have your audio input, and you figure out whether it has a voice in it or not. If not, then it's silence. If it does, then you decide whether it's the word that was spoken, is it in your vocabulary, in which case it's one of the known words, or it's outside your vocabulary, in which case it's one of the unknown words. I'm not saying this is the exact processing flow. This is more just the concept of what is silence or not. Silence, again, is not something that's just like really quiet. There were some files that were like completely zero all the way across. That's silence for sure. But there's other files that really, I'm sure, want to be labeled as silence, but they're noisy, like they're really loud, but it's just like random noise and nobody's talking. So we didn't get a super clear explanation of that. All right, now we're dealing with audio, and everyone who deals with audio has a few choices to make about what features they want to use from the audio for a competition like this. And it falls into roughly 3 categories with lots of variations in all of them. The first is you could look at just the time domain waveform. It's basically a time series of the amplitude of the sound. So that's time running along the x-axis. And just work with that. It's one-dimensional in the sense the time series is one-dimensional. And so that's interesting. Most people who work with speech or audio generally hardly ever use that. But in the last couple of years, there's been some really interesting work that does start with that. So people were interested in trying that out. But the other alternative is to take that time domain stuff and convert it into a spectrogram. So again, we've got time running along the x-axis here. But on the y-axis, instead of being amplitude, now it's frequency. So you're just seeing how do the frequencies change through time as the person's saying something. So this is actually the spectrogram for that utterance, which is the word yes. So you can see there's a burst of frequency activity here, and then it changes in character as they get to the end of the word. So that's cool. Very common to do that. Lots of variations. The spectrogram, you typically work with the amplitude of the spectrogram and maybe the log of the amplitude of the spectrogram. You don't necessarily want a linear scale for your frequencies because that's not like how humans hear, so they'll do it more on a logarithmic scale. They'll go even one step farther than that, which is they'll look at it on a logarithmic scale, but also kind of group together frequencies in these sort of buckets of different sizes. Again, all inspired by the human hearing system. And this throws out the phase information, which this doesn't, the time domain. That's one of the reasons people are interested in time domain. This one, it's really hard to do anything with the phase, so you just throw it out and work with the magnitude.
Basically three-dimensional then, with the phase, right?
I wouldn't call it three-dimensional, no. You're just taking something that's 2D and making it 1D. Well, that's wrong too. This business of grouping the log frequencies together is called like a filter bank. There's a very popular one called the log MEL filter bank, or that's how people refer to it. So I just mentioned that because you'll see that coming up a lot in people's solutions. The details are not too important. I want to focus more on the data science part of this than the feature extraction parts. And the last one is MFCC, which is MEL frequency Kepstrel coefficients. It starts from this, but applies a discrete cosine transform. If you're familiar with the concept of principal components analysis, PCA, there's something like that. You apply a DCT to this. It has a bit of a decorrelation property, and it lets you do some dimensionality reduction. So this is a lot of data to deal with. The MFCCs, you can, in some sense, it orders from the most important things to the least, and you just pick the most important ones and work with those.
With PCA, there's a linearity assumption. This said that also. I mean, like it's an alternative to like an autoencoder.
It's, I wouldn't go that far with the analogy. It's just, yeah, it's just a transformation that has the properties that PCA does of kind of picking out your important stuff. And you can keep as much of that as you want. Yeah. Sorry, you did, or Matt does, or
Yeah, I do. Did you see anyone use architectures that used like more than one of these?
Yes, all of them, although not in a single model.
Okay.
Generally, but in terms of combining models, absolutely. Yeah, we're going to see ensembles like you wouldn't believe. Yes?
What is the meaning of the colors of the MCC?
This one's easier to explain. It's the magnitude. So, I mean, this is really, there's sort of a third dimension coming out of the screen of the height of this. So the bright color here means that at this time and at this frequency, there's a lot of energy at that time frequency point. Whereas over here, these dark colors mean at this time and there was very little energy at that frequency at that time.
What about the bottom one?
The bottom one's a little harder to interpret. Certainly, I mean, there's a scale here that has something to do with magnitude, but because it's gone through this transformation, it's a little less interpretable.
So is it just like another dimension that you're interpreting as?
It's like, well,
It looks like 0, then blue is negative, then red is positive.
yeah.
Maybe like another dimension that comes out of the screen.
Yes, in the same sense that this is. I mean, this is really a surface with hills and valleys in it. And this is as well. It's just these hills and valleys are easier to describe what they mean. This one, it's a little less clear. Yeah, Anshan.
So is the best way to say that is that they are quantized energy in MEL filter banks? So you sort of group the energy in the different filter buckets, right? So
Yeah.
the color would then be the energy in that particular.
Well, certainly, I mean,
One of the points.
yeah, I know. Well, what you said, I'll buy it for this, where it's telling you how much energy. This one, it's some sort of, I hesitate to even call it energy, because that's a physical term. Here we've transformed it to another space, just like in PCA, like you end up in some other space, right? Yeah. So the DCT here is just taking you to some other space. Yeah.
I'm trying to figure out the Fourier transform. From what I'm familiar with, if you have like amplitude versus frequencies.
So
How much of each frequency?
correct, but what they do is to get to the spectrogram, you take a small window of time and you do the Fourier transform and in that window, and then you move the window and you do that sliding window. That's why, I don't know how well you can see it, but these are fairly coarse. These are rectangular points and they have a width of about that, which you probably can't see, but that's the time window. Typically 32 milliseconds. They do the Fourier, it's called a short time Fourier transform, STFT. You do the Fourier transform over that, then you move along to the next one. And that's how you get how the frequencies change through time.
Are they overlapping?
Yeah, typically they overlap, yeah.
So it's almost like a convolution.
It's not like a convolution. It could implement it that way, but I don't think it's the right way to think of it. Was there another question back there somewhere? No? Okay. Good, you're asking lots of questions. It probably means I won't get through all my, well, we'll see how it goes. So, as I say, people used all three of those features, and we'll hear lots more about that, but just to look at it, if we look at more examples of just the spectrogram for 3 different words here. Across the top, it's yes, cat in the middle, left at the bottom. I think you can see what a challenging problem. Like there's just, how would you know that this is the same word in these 5 things? Like human beings are terrible in interpreting spectrograms. I know somebody was trying to do it once, was trying to learn to, yeah, there's people who can do that? Wow, that's amazing, yeah. So, and they could actually interpret words from looking at spectrograms. Good for them. Yeah, wow.
You can like recognize noise sometimes, right?
Oh, sure, there's lots of things you can recognize, noise versus words, but to actually identify which word is being said here, that's tough. You think that's the? Well, you're wrong, it's cat. See how hard it is? Back on the class distributions for a second. Here's the actual distribution of the class labels. For reasons I don't fully understand, the ones that are a little bit lower here are the ones, I'm pretty sure it matches up to, nope, I was gonna say it's ones, it's in our target set of 10. Anyway, for some reason there's this bimodal distribution. But it's, it's not crazy. It's not crazy until you group all the unknowns into one category and then get that big spike. It's always helpful to know what the distribution of your classes is to the training data. It would be great if you also knew what it was for your test data. But of course, you don't have labels for the test data, so you're kind of stuck. Or are you? Well, here is a data point which nobody should take too seriously, and as a competitor, definitely not. Leaderboard probing. So what people would do is they would submit a prediction file, which is all exactly one thing. Like they just say, okay, everything's unknown. What's my score? Everything's stop. What's my score? So they do that for all of them, and that score is basically telling you what percentage of labels are the one word that you picked out. Lots of problems with this. First of all, starting with it's borderline illegal, I think. It's not super much in the spirit of the competition, but whatever. I don't think there was an explicit rule against doing something like that. The other thing is they did deliberately pollute the test data with a lot of stuff that was not going to be used for the evaluation, so that's going to screw up your statistics. Another thing is that this probes what's known as the private leaderboard. So out of this 150,000 samples that you have to predict on, you submit, while the competition's going on, you get a score to see how well you're doing. But that's off a small subset of the full test that you submitted. So you're getting statistics from a small subset that's deliberately being mangled, and there's also sorts of reasons not to take this too seriously. However, the fact that it came out moderately balanced, that's encouraging. And I think, again, it's testimony to the contest organizers to not do some crazy imbalanced thing. Yeah?
I'll say so. I was chatting in the Slack about this a week or two back, and so I've been doing work with an imbalanced training set, or maybe more accurately, a situation where I know that the class balance of my training data is not the same as my test data, and that's a really powerful prior, and you can really change your predictions if you know that. And so I think this is really important.
It is, and in the real world, you really want to know, because the models learn the data distributions. among all the other things that they learn. And so if you get that wrong, you're making life really hard for your model. And if you get it right, you're helping it along. Okay, a couple of data challenges. I said it was not many problems with the data. There were some small problems with the data. I think they're small. There's the problem that came to be known as the unknown unknowns. So there were words in the test data set that were not in the training data set, even like in the full group of 30 words. So, so back to the training data, you got 30 words, 10 of them, we have to predict the other 20. Those are unknowns, fine. But then there's other words in the test data set that aren't part of any of those, different from all of those words. Those became the unknown unknowns. There was a lot of consternation about this in the competition. I don't think it was that big a deal. It's certainly in the real world, if you're actually making an interface for people to talk to say things to, they're gonna say all sorts of crazy stuff. You've gotta be prepared to just flag it as unknown, no matter whether you've ever seen that utterance before in your life. I think, no. Certainly, when we looked at the outputs of our models to see what the class distributions were on the test set, the models are imperfect, but it's probably a decent representative. There was the unknown category dominated by far. How many were unknown unknowns? Yeah, didn't really. It's hard to get those statistics, right? Because you're not classifying them, so you don't know which are they known unknowns or unknown unknowns. As I say, I don't think it was a big deal. A bigger problem was the second point, that validation and leaderboard scores were wildly divergent. So, and this is why I said I listened to a lot of these files. I just couldn't believe what was the numbers I was getting back from the evaluations. So I would listen to a lot of things. I'd do a spot check. I'd listen to a couple of hundred, and I'd classify them myself, and I'd match it up with what the model said. And like we were getting like 95% accuracy. You put it on the leaderboard, and it comes back 85%. Everyone had that problem. I still don't understand why that was the case. And I don't think anybody really understands whether that was some accidental artifact of the way the competition was set up. However, it was kind of annoying because it meant that you couldn't do a lot of testing locally with the confidence that it's going to change your leaderboard score. And if your leaderboard score went up or down, you weren't quite sure whether you're really doing a good thing or not. So we got to the point where we just said, you know, we're going to forget the leaderboard because we can't trust it. When you get divergences of anywhere from 5 to like 12, 15% between your local measure and the leaderboard, you just have to do something else.
Okay, I want to talk about class imbalance priors again. So if your training set is like 2/3 unknown, I think maybe that's roughly what it was.
Yeah, even more.
So your training data is actually like an easier problem than your test data, because your test data, at least on the leaderboard, is like evenly spread over 12 things, right?
Yeah.
And so like if I come into a quiz and I like a multiple choice quiz and I know that 75% of the answers are C, like I can actually score better on that without knowing any of the answers to the questions. So that may have been a big driver of that.
It may have had something to do with it. This is also why people were worried about the unknown unknowns, because we trained on the unknowns, and then our validation set is on the unknowns. So I think some people took out some of the unknowns to try to predict the unknown unknowns. People did all sorts of stuff. I don't think it amounted to much in the end. Ducky?
You could make your own unknown unknowns by, say, running it backwards.
Yes. So people did things like that, run the file backwards. And although that was my first thought as well, then I looked at all our models, and they were actually invariant to time reversal. So that wouldn't have helped. Like, even if it's an LSTM, which has some time type stuff in it, they will be LSTMs. So you reverse it, you're going to get the same answer. However, there's other tricks, and I won't spoil it. We'll come to that. One of the winners did a clever thing for unknown unknowns. Yeah, Matt.
Oh, I was going to ask, did you see anyone trying to optimize for something that wasn't accuracy, given that it's really unbalanced in training? Not in test, like MCC might be a better metric.
No, I don't think anyone did anything other than just straight accuracy. Dennis?
Yeah, actually talking about this distributions, classes. Actually, in the test set, there were much more unknowns, and that not 10% as we can get from a leaderboard probing. It turns out that to calculate the score, organizers took different percentage of different classes. So they, like, let's say, public leaderboard is 30% of all the data set. Yes, 30%, but they include only like 5% of unknowns in this 30%. Am I right? Kinda.
Yeah, something like that, yeah.
Yeah, so unknowns, like there were much more unknowns than 10%.
Here's, this isn't a very good model, but it's just a model that we trained. Here's the distribution of labels that it came up with for the test labels. So this huge, almost, well, 58% unknown.
But if you submit like all unknowns, like
Yeah.
all classes unknowns, you won't go.
You won't get that, no.
57%, you'll get 9%.
Yeah.
And this is another thing.
Which says that all these unknowns are the you know, the data they polluted the test set with. They just threw in a bunch of unknowns.
So the test set is comprised of public leaderboard, private leaderboard, and junk, right?
Yes.
And are you telling me that you think actually the private leaderboard and the public leaderboard had a different distribution?
Nobody knows, and yeah, there were suspicions about that. In the end, though, there was no leaderboard shakeup at the end, so it's probably fine. Kenneth?
So how can you like incorporate the distribution into building your model rather than validating your model?
Sorry, say that again?
How can you exploit like the distribution of your data? In building the model instead of.
I guess the easiest way to exploit, if you really knew the output distribution, you would sample from your training data with the same distribution, and that would help the model learn.
So
Or-
I thought a lot about this. I also talked to Kiri, and if anyone knows Kiri, they probably respect this outcome then. And so I'd love to talk about this over drinks later, but you can do some sort of Bayesian adjustment where you can say, like, my model had this prior during training, and I have this prior during test, and therefore I can modify the probabilities that my model puts out with essentially a new prior, and then you can create like essentially a wild adjusted.
Instead of magic numbers.
Yeah, I mean, it kind of looks like magic, but I think it's justified.
Yeah, now that you mention that, I've heard people doing that. Yeah. Anshan?
So given that you were evaluating with a subsample version of unknown, could you create, so if you think about it, you could create your training data set such that you're sampling a subset of your unknowns, right? It's just that training, you'd be training with multiple data sets, except that the unknowns would be 5% instead of the whole thing.
Mm-hmm.
You can do that over and over again because the test scenario is again unknowns, but it's just that it's sampled from a larger population. So
Mm-hmm.
was there any sort of sampling technique that one could use to create data sets during training?
There was lots of data augmentation, and we'll hear more about that shortly. There were some data augmentation specifically to generate unknowns. I might as well tell you that now because it might get lost later. So instead of flipping it backwards, because that's not very helpful, people would take two files and put them together in such a way that you kind of had two words, like not necessarily right. I don't think it like right on top of each other because that wouldn't be that great, although it's something, but it's sort of one after the other, and generated a whole bunch of unknown data there. So that's data augmentation. There's a question of, well, what do you do with that? What sampling distribution do you want to use? And it really came down to two things. That people just used the natural distribution that came with the data they got, or they did a scheme where they just sampled in a balanced way. I sort of thought that the test distribution was going to be balanced, and so we started out with doing balanced sampling. Later on, I switched to unbalanced and didn't make that big a difference, as it turns out. Right. Okay, so that's a whole bunch of background. Let's talk about the solutions to this. Oh yeah, thanks. I skipped over that. So this is the competition host said, oh, sorry, didn't realize so much of the data was mislabeled. Please let us know what you found. And people helpfully put up lists of things that they'd found that were mislabeled. One of the organizers went through and listened to every one of his validation set samples that was misclassified by his trained model. So that narrowed down, I think it was like 2,000 things, and he just listened to every one of them and said, yes, no, you know, what was right, what was wrong with the given labels. Anyway, but he only found a couple of percent that were wrong. It's not huge. Any data set's gonna have a few percent of just bad labels. So I think, you know, the host would love to have a higher quality data set, fair enough, but I don't think there's anything to be ashamed about with the quality of this one. So just before we talk about the solutions, we're going to talk about the solution approaches, because it became pretty clear early on that sort of working with the data in clever ways, in innovative ways, and I'll call it model tuning, but that's probably giving somewhat the wrong idea. That's more important than the model building. I was kind of hoping, well, what we've often seen in these competitions is that there's maybe a traditional way to do things, and deep learning comes in and some amazing network model that somebody comes up with and just kind of crushes it. That didn't really happen here. There are many different types of models that you can apply, and if you've done any work with CNNs and RNNs, they would all sound very familiar to you. So in fact, I'm not going to spend a lot of time talking about those, except in a very high-level kind of way. But the amazing thing is, they all gave about the same accuracy. Didn't matter that much how complicated your model was, didn't matter that whether you were starting in the time domain, or with a log-mel spectrogram, or with an MFCC. Everybody, you could do all that, and you kind of get 86, 87%. And then you kind of hit a wall. One or two people pushed through that wall with a single model, but mostly not. But,
What was the model that you say pushed through it?
oh, you'll see, you'll see. It's a little too hard to summarize in a sentence, but you'll see. But it does leave you in this interesting situation where you have a whole bunch of models that are substantially different. They take a different approach, they're working different features, all these things, and they're all making their own estimates. And so a lot of the fun part of the competition was, okay, well, how can you exploit the fact that you have multiple estimates? I may have said all this already, but in terms of the single models, they used all the features, generally CNNs and RNNs. And then there was a whole bunch of things I call fancy techniques. So a lot of these are, I say there's lots of newish things. Some of these were pretty new to me, and this is what made it fun to read about in the solutions afterwards. A variation on standard ensembling, model stacking, distillation, mix-up, various kinds of augmentation, pseudo-labeling. Some of these things I'd heard about, I've never seen them done in practice, so it was fun to see what would happen there.
So what's square root ensemble?
You will see in a second, yes. I'll talk about each of these a little bit. Now, I know for many people in this room, you probably have a half-decent idea what many of these things are, and certainly what ensembling is, but just to, because not everybody does that, I want to indulge me to be a little pedantic for a slide or two to explain how this works. So the classic way to think of ensembling is the competition where there's a jar full of jelly beans and you have to guess how many jelly beans are in the jar. And if your guess is the best, maybe you win. But suppose you just wanted to know what's the best way to come up with that estimate without actually counting them all. Well, if every person in this room had a chance to look at that jar, they would come up with an estimate. And their own estimate would be the right number plus or minus some error because it's an estimate. As long as the errors are sometimes too high, sometimes too low, if you took everybody's estimate and averaged it, those errors would tend to cancel out, and that final average would be a much better estimate of how many jelly beans in the jar than any individual's estimate, likely. Certainly most of the individuals. That's ensembling by doing averaging. The concept of what we're doing with these models for this speech recognition competition is no more complicated than that, for the most part. That's the most common way to do it. The other thing I want to spend a little time on, just because this terminology is going to show up again and again in the solutions. Here's the general idea of what's going on. This is a bit step up from the jelly bean jar, but let me walk you through it. So here's how the classification typically works with these neural networks. And everyone did pretty much this. This is a very high-level description. So at the left, we got XI. That's the input training data. That goes into some network, CNN, RNN, some variation on that, whatever. At the last part of that network, it spits out numbers, Z1, Z2, down to ZC. C is the number of classes that we're trying to predict. It'd be 12 in our case. And those numbers by themselves are not interesting. You put them through what's called a softmax function. Just means you take the exponent and then you divide by the sum of the exponents across all the classes. The net result of that is you get a bunch of numbers, which I'm just going to rename P1, P2, P3 down to PC. They sum up to 1, which means you can interpret them as probabilities. And when you want to figure out your label, you look at the probabilities for each of the different categories. You pick the one that's the biggest, that was down, and you say, therefore, it has the label down. So one thing to appreciate is that to get to that final label, you're actually throwing out a lot of information that your network is trying to tell you. You have all these probabilities for one thing, and they can be all over the place. Some of them might be close to each other. And even before the probabilities, you've got these numbers which feed into the softmax. These are called logits, and that's not a term you run across a lot, but there's a reason I want to use that name here because it shows up in one of the techniques specifically. All right, so that's classification using softmax, and as I say, the back end of everyone's network looks something like that.
Logic's just the S function with the exponential, right?
It's like the inverse sigmoid or something. Yeah. It's the thing that feeds into the softmax. For our purposes, is all we need to know. All right, so back to ensembling. We're just doing the jelly bean jar thing here, but just now we've got multiple classes, and we're trying to estimate a number, trying to estimate classes. So model 1 gives us a probability for each of the C classes that we're interested in. Model 2 gives this its estimate of the probability all the way down to model N. The easiest way to combine those together to come up with an ensemble estimate is to just average over each of the classes, average over the models for each of the classes, and that gives you your ensemble. That's everybody who did that, their scores went up by a couple of percent. Their accuracy went up by a couple of percent over any of the individual models. It's just how it works. It's always good for accuracy. But here now, this is the answer to your question, Izzy, about what is square root ensembling. The first place winner, instead of just taking the sum of the probabilities and averaging, he averaged the square root of the probabilities. I don't know what the theoretical basis for that is, or maybe it's just an empirical basis. A couple of people asked him in the forum, and he never really got around to answering. Why, I don't know, maybe somebody in this room knows, but comment, question here?
I think you need to take the square root of the sum afterwards.
Take the square root of the sum afterwards?
So square?
Square them? Yeah. That would be a sensible thing to do. That's not what they did in this case. They actually took the square root. Now, what's that? It would be a better estimate.
All you care about is the highest one. So when you square it, the highest one is still the highest one. So
Yeah.
You're right, it'd probably be a better number, but it wouldn't make it more useful.
Yeah.
Relative to everything else, if you didn't take the square of all of them versus if you took the square of all of them, it would come out with the same.
Yeah, in relative terms. I mean, any monotonic function is going to have that property. All I can think of here is sort of an intuition, is that the square root function will tend to kind of compress probabilities that are high and stretch out ones that are low. So you'll learn more from the other probabilities that are somewhat farther down the list. But I don't know, Matt.
So using what you just said, it might be this empirically. we're going to assume that pretty much all of these neural networks are going to be overfitting, right? Because that's
Mhm.
what they tend to do.
Mm-hmm.
So by taking the square root of this, it might reduce a little bit of the overfitting. So if you have two networks, for example, if you have three total, you have two networks that are pretty sure that it's one thing, and then one network that's really sure that it is this other thing.
Mm-hmm.
The two would take over the one a lot easier if it's square root.
Yeah. So these are all plausible explanations, but I think it probably comes down to an empirical result as opposed to something. If we assume all the statistics are Gaussian and blah, 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 the average is the best estimate. It's the optimal estimate. This is an optimal estimate for some distribution. I'm not sure which one. Yeah.
Well, I'm thinking if someone had a lot of time, unless the square root is based on some kind of mathematical theory, one could use this power of 1/2, like instead of 1/2, have it as a hyperparameter.
And then train on that.
0.6,
Yeah.
0.7.
Sure. You could learn what the power is that gives you the best results. Yeah, for sure. I wouldn't be surprised if some people are doing that right now.
Maybe when you're using floating point numbers, and like certain places you lose accuracy, and then even certain orders you lose, like adding, for example, floating point numbers is imputative, right? So maybe it's doing some triple floating points or something.
I'd be a little surprised if floating point precision is playing a role here. But
you are right. You do. If you start doing things like this, you have to watch out for like numerical. I remember doing ensembling like this that was causing my small numbers to become too small, or
yeah,
around my large numbers too large, and it became unstable.
things can blow up. Yeah.
There's different tricks people do sometimes to make the numbers not disappear, or like. So I mean, like this could be something like that.
Yeah, I think it is to some extent. I don't think the disappearing thing is super severe, but this has the ability to change the relative distance between these what used to be probabilities. These aren't probabilities anymore, by the way, because they won't sum to 1. But he didn't care. Doesn't matter. You can still pick out the biggest one, and that's your label. Yeah, Bruce.
Was there significant overfitting?
Nobody talked about it a lot. Certainly in our models, we were, you start out overfitting, then you do something about it, so it gets under control. It wasn't a huge problem. Batch normalization is kind of magic. That helps a lot, and just drop out and stuff. And you just do the usual things that usual once you've been through this, and that'll seem to help.
So if the winner was doing this, does that mean they weren't stacking?
Oh, they were doing everything.
Okay.
So speaking of stacking, we talked about one way of combining your estimates, which you average, or you average the square roots or something. Another somewhat more sophisticated way is what's known as model stacking. This used to be like really popular in a lot of Kaggle competitions, and I don't know whether it's just become so routine that people don't comment on it much, but I haven't seen it discussed as much in more recent competitions, and it only came up a couple of times in what people were doing here. The general idea is, and this is going to be really brief, and unfortunately all the notation has changed from the last slide, which I'm sure you have memorized. So you start with the original training data. You've got all these models, which are called the level 1 models. They're all just independent models that you put together in all these different ways. That gives you a whole bunch of outputs, all the predictions from those models. And then what you do is you create a level 2 model, or multiple models, again, where now the training data, the input to this, are the predictions from your level 1 models. So these become, the outputs become features, basically, which are input to this model, and then you train this model, again, using the same ground truth that you used originally, and that gives you your final prediction. Yeah, Bruce?
Is the level 2 model trained on the validation sets?
You do it in a very particular way, so that you don't get a lot of sort of data leakage between things, but these references actually talk about it quite nicely. But essentially, you kind of do a k-fold split of your data, and the features that you use here are the ones that are predicted on, that held back fold, essentially. So yeah, I've certainly oversimplified it here, but if you do it carefully, then you're doing it in a way that this model can actually really benefit from the places where these models, like this model may be really good on some parts of the data, and this model is really good on different parts of the data. If you set this up properly, you can really pick out just the best of all those input models at your level 2 stage.
Are the level 1 outputs ensembled in any way before they're fed into level 2?
No, no, they go in pretty much raw. So here's a variation on that, a very significant variation called knowledge distillation. This is Jeffrey Hinton at work and some colleagues. This is a fairly recent paper. I thought this was really cool. This is one of the nicest things I've read about in some time. And Jeff Hinton in his papers, he has a very elegant, almost poetic way of framing the problem and describing what he's doing. You read all this, and it's kind of like the capsule stuff, right? You can get swept along by the poetry of the description, and you think, wait a minute, can you actually make that work? And so this works. In this case, the setup is similar. We have all our training data, a whole bunch of different level 1 models, a whole bunch of outputs. Now, though, we don't train on the outputs. Instead, we train a completely new model called the distillation model, whatever, starting from the original data. And this is now the target. These are the labels. This is the ground truth for what you're training against. So again, model stacking was you took these, you trained your model to, and again, the ground truth was the same as what you used to train these models. Here you're throwing away all the ground truth. Well, you don't have to, but you can. Conceptually, you can throw away all that and just try to predict in this model what all these models would have predicted. So it's not obvious why you would do that or whether it would work, but it helps a lot. It helps a lot because this model can be quite small, and it can capture all the benefits of ensembling without becoming gigantic. This is what the first place winners used to get their Raspberry Pi solution. They had, I don't know, 30 different models. They did this distillation. The distillation gave them an accuracy that was as good as their fancy ensembling thing, but they only had to provide a very small model. I highly recommend this paper. I'm going to suggest it for the reading group. It's really nice. He has a lot to say about why it works and how you do it. Yeah, Anshan?
Is one of the reasons because you get enough variety in your outputs here that Hinton loves to use noise as a regularizer. So does it introduce enough variety and
well,
that it regularizes against?
Let me show you one more slide about this because it's, there's a little more to it than what I described. And the reason I focus on these logits is because he actually takes, not the labels from his level 1 models, not the probabilities from his level 1 models, but his logits. And he recomputes the softmax, but this time with this factor T, which he calls temperature. And this kind of goes back to our square root ensembling a little bit, because what happens with T is, as T gets bigger, as the temperature goes up, that tends to flatten out the differences between your probabilities, your prediction probabilities. Hinton and his co-authors, their argument was that there's a lot of information in those probabilities. If it's, say you're doing it on MNIST, which is digits, the fact that an 8 can easily sometimes be mistaken for a 4, that's actually useful information. And to just stick with the label 8 doesn't tell you anything about the fact that it often looks like a 4. If you do this, then the relative probabilities show up much more. Things that would otherwise be like really low probability are now sort of elevated in their importance. I mean, relatively, they're still less than the correct ones, but it's there. And they argue, again, not with a huge amount of theoretical justification, but that lets you learn something from the distribution of your predictions and not just from the single label. Yeah, Kenneth?
So how is this different from like quantum annealing? No, what was it called? So simulated annealing stuff, where like maybe on the SVG, like we're doing the present the sense. I can present temperature. How is it different?
Yeah, I don't think there's much of a connection there. I mean, maybe, and I don't know that much about simulated annealing. I think of it more as a way to inject a little bit of randomness into a model to knock it out of a global or a local minimum. This really is not like that. This assumes that your initial models their local minima are good enough and so on. You just now, how can you distill the information of those models into something that's much more compact than usual? Ducky?
How do they choose T? Do they vary it?
It was empirical again, I think, yeah. They didn't learn it except through some experimentation, yeah.
So now the output of the distillation network is a vector, I guess, for each example?
So the output would be, yeah, so at test time, you feed an input and you're gonna get probabilities as output because that's what it's training on. Well, it's training, sorry, you get these.
And then you do the softmax on that?
And you do the softmax on that, yeah.
Right. But you have multiple models, right? So are you...
Not anymore. So you don't need your initial models anymore at test time. That's the beauty of it. So the problem with stacking is all those models that go into the stack. At test time, you want to feed it some new data. You got to have all those models around, have them do their predictions, and then you ensemble them together. That's a huge amount of data you got to carry around and takes a long time. This one, no.
It's a compression technique for the models.
Yeah.
Well, it is, but that's...
I'm just thinking about, like, the output of the distillation, though, isn't just, like, one set of logits. I thought it'd be logits for each different model.
No.
If you go back maybe just one slide. So like, these are the targets?
Right.
And
Yeah.
so, like, that's kind of awkward, right? Because there's many of them.
Yeah, that's true. So you still have to put them together somehow to get the right dimensionality out of it.
So you just have more, they just become new training samples. So for each example, if you have n of these models, right?
Yeah.
So now instead of having one output target label, you have n output target labels. So you're basically replicating with different.
So you randomly sample from that, basically, like for your target.
No, you're not randomly sampling. So I mean, your ground truth is one example and one probability.
But there are m probabilities.
Yeah. So if you were to do a one-hot vector encoding, if you had zeros and ones. So if you knew what your label was, right? So that's still.
M is not classes, model, number of
M is models.
Yeah, but now you don't have that one example. You have, for that one example, you have n different hypotheses of what it could be. So you're in some sense expanding your training set, right? Okay. Does that make sense?
I'm going to ask you to continue that discussion over beer. I'm running way over time here if I want to get through some more stuff. And
You have 38 minutes left on this battery.
you're on battery? Why are you on battery? I forgot to plug it
I
in.
did not set this up.
Well, that'll definitely be a hard stop. I told Rogue we'd be over there at 8 o'clock, so I'll need to zip through some of this stuff. But clearly, a lot of people in this room will vote for this paper in the reading group. It's really nice. And we're at the limits of my understanding of it, so I couldn't answer any more questions about it anyway. Okay, I said that. The advantage is it's small. Training and test time augmentation, a very common technique is to fiddle your training data a little bit to create something that's similar, should have the same label, but it gives you more training data. Very common in this competition was to add noise, you just mix it in, you time shift a little bit, or do like a speed change. Either speed change or time stretching. These are things you can do with audio. There's library functions to do it. One person claimed by those sorts of augmentation, or that last one in particular, he added a percentage point on the leaderboard. That percentage point is a huge, huge number in the scheme of things here. Test time augmentation is also a very powerful technique, often used, and certainly in this competition, where you do all of that data augmentation, but you do it on your test samples that you have to predict for, and each one of those augmentations gives you a different answer, and then you average those together. All right, here's one of the new things to me. These folks called it mix-up. This is really weird. This is another one that's worthy of a paper reading group. Not very theoretically justified, but certainly interesting. It's sort of in the category of data augmentation. Instead of training on single samples, they train on pairs of samples. And what they do is, so for these I and J just index a pair of samples that you choose at random. You actually do this weighted convex combination of those samples. In the case of these audio files, I mean, you're literally summing up the audio file. So if you listen to it, it would be like you're hearing two words at the same time with weights between. They also do the same thing to the labels. How do you do that? It's you one-hot encode the labels, basically. And so you can say the label is a little bit I and a little bit J. And you just train based on that in all the usual ways. Only a couple people did this. I'll have a little bit more to say about it in a minute, but it worked like really well. It's very surprising. This is quite a new paper. Some folks at Facebook published this recently. So that definitely deserves some more exploration. Pre-processing, we talked a little bit about that. Ladder networks, another paper I'd like to read. I don't understand it, so I won't say any more about it here. Pseudo-labeling, super interesting. Again, so counterintuitive. You build a model, you train it, you make all your predictions on the test data. Well, that gives you a whole new set of labels, doesn't it, on the test data. You take those labels and you train either the same network again or a different network. It sounds crazy, sounds a little too circular or incestuous or something, but people got some really good results by doing that. You would think so, but it seems to help. And the sort of hand-wavy justification is that it gives the models more data structure, helps them learn the structure of data just because they have more examples to work from. Yeah, Bruce?
Especially if you add noise, then it can learn from all the variations of that.
Yeah, but add noise to the pseudo labels, or?
Especially if you add augmentation.
Augmentation noise is good. No, all the other augmentation things are absolutely fine. It just this particular thing is weird. All right, lots of solutions. I definitely don't have time to talk about all of these, but let me talk about a couple of them. So the first place, folks, 30 models. They used all the different types of features. Their best signal models were 86 to 88%, like everybody else. And they did do some pseudo-labeling. When they balanced their class sampling, I didn't see this in my work, but they say they got a 2% improvement in their models. That's 80 to 82%. That's obviously in the early days of, because that's not a very good number. What's interesting out of this? Pseudo-labeled based on label noise. So here's one way that the pseudo-labels sound a little less mysterious. You have all these models that you're doing. They're giving you different estimates, and so they're giving you different labels for the test data. Some of those labels will all be the same from all the models. They'll all agree, and other ones they'll be in violent disagreement about it. If you stick with the ones where they all agree, those are probably good labels. And so people would filter the labels they'd use for the pseudo-labeling based on that, and these guys did. Model distillation won them the Raspberry Pi prize. Their test time, it runs in 60 milliseconds. The threshold was 200, so they are well under that. They did test time augmentation. Sorry? For one word, yeah. And I mentioned the square root averaging that they did there. Second place solution, this one was different from almost all the others because he had basically a single model. He says, I don't know anything about ensembling, and I didn't really have time to understand it, so I just did this, and he gets second place. So he got close to 91% on the private leaderboard using a single model.
That was a square root.
No. Well, he also used the square root, yeah. But minimal ensemble. He didn't get much out of his ensembles. And the reason he used square roots, I can tell you, is because the first guy told everyone to do that, like way early in the competition, so everyone just started doing it. So he used these log mel filter banks. That's a flavor of the spectrogram. he felt it was important to treat the time and frequency differently, and there are good reasons to do that. If you know something about neural networks, this will make a little bit of sense to you, but it's, it's a few layers with some max pools, and it's just a little bit, the aspect ratio is not 1-to-1. Yeah. Sure. Yeah, he didn't, he did the convolution all at once, but his convolution kernels would be not square. They would be a different size. And the numbers in brackets here are the sizes in the time and frequency direction. So his max pooling was, different. He just did it differently. Who knows how he came up with these particular numbers?
And the spectrograms were the input.
Yeah, in his case, it's the log-mel spectrograms. And he did a couple of fancy things. He got 1% out of vocal tract length perturbation. Another Jeff Hinton paper of all the crazy things. I didn't look at that paper. Would love to know more about it. Third place solution, kind of similar. The best single model was 87%. Ensemble didn't help that much. The key for them were these semi-supervised techniques like pseudo-labeling. And with some sort of weighted average that I didn't fully understand. When they used the pseudo-labeling, he did 100% of the training data, but only 20 to 35% of the test data. So it's still mostly the training data, just throwing a little bit more. This was kind of interesting. The second way he did this semi-supervised was he called a pre-trained model using 100% of the test labels that had been predicted. And then he went back and did another training using all the training data instead of the test labels. He said just one epoch was enough to sort of prevent the overfitting problems that might have come up. That's a weird technique, pretty awesome. I'm going to skip over these unless there's something super interesting. We hear about model stacking. Fourth base solution, all these levels, I talked about in stacking, the level 2 models, like these guys did everything. Oh, the fourth place solution, I don't know if it was a team or one person, but they should get the prize for the most work. Like they just kept doing more and more stuff. The test data set was very strange. That was their comment there. 7th place solution, more and more. So you know what, I think I'll stop there. I've got more slides, but let me actually skip way ahead. Just some random things that we learned about in doing this competition. So these are tips about how to work together as a team and just how to approach all this stuff. Super important to talk regular as a team. We had a daily call, basically. It might have been short, but a daily call. In between the calls, we'd use Slack and all the usual things to talk.
Video call?
Yeah, but didn't matter. But it mattered to the extent we could share screens and show data test runs and things like that. So that was helpful. Trello, free tool that's great for keeping track of tasks. So our particular team, we were kind of gung-ho in the first half of the competition, and then we all got busy with our other jobs. So we basically dropped out of the competition halfway through. So our Trello board is full of all these things that we were going to do, but we never got around to. There's no shortage of ideas. This one's a little more subtle, perhaps. Keep all the data. Keep your predicted labels, keep your probabilities, keep your logits. It's not enough to just create your submission file and then never be able to reproduce that again. You want to be able to reproduce it, and if you're going to use knowledge distillation, turns out you want to keep a lot of the much richer output than just the predictions. One of the guys in the team realized it was just a good idea to do a git commit every time you do a submission. That's a good way to be able to reproduce, and easy. It gets really hard to just do the bookkeeping around these things. You're trying so many things, and it's such a hassle to make notes on stuff. Just do a git commit, and you can get back to it. I did use multiple GPUs at one point. I got about 1.5x speed up, and then some code that Dennis wrote broke it all. So I had to back off from that. So it wasn't spectacular, but it was okay. Notebook tricks, get the extension that lets you collapse heading. Oh my God, that's so good. That'll change your notebook life. NBDime is something that will let you manage notebooks in Git without it being completely crazy. TensorFlow has a there's a sort of a contrib stuff, libraries there. It has lots of good audio stuff in it, it turns out. We were surprised. We didn't learn that until fairly late in the competition. That's good. FFmpeg, which is a tool that if you do any work with video, you would know about it. It turns out it has some really good audio stuff too, and I got some value out of that. Additional references. Okay, we're more than done. That's it, folks. Thanks. Now, is there any last burning question somebody really has to ask right now instead of asking it over a beer? If not, we should pack up and go. Please reassemble the room into the state that it was in when you got here, which is a 2x2 array of tables with chairs on both sides, all the way down. And we want to leave it in the state that we got it in. You can stop the stream now. You did stop it, and stop the recording too.